In this problem, we're asked to factor completely, and we've got a pretty complicated polynomial here with 4 terms and 2 different variables. And let me slide over for a second to show you this is going to need several factoring techniques. So I've got 3 different examples that all get wrapped into the solution of this problem. Well, always factoring out a GCF is a good idea. So I can look at the numbers first of all, 3, 3, 27, 27, and so the GCF there is a 3. And then I can look at the x variables. So I've got x cubed, x squared, x, and no x's here. So there's no x's that are in common for all 4 terms. And then y's, y squared, y squared, y squared, y squared. So that's in common between all 4 terms. So now I'm thinking about what's left if I factor out 3y squared. I'm going to go ahead and check by distributing, make sure I got that right before I move on. Okay, looks good. So now this is easier to deal with. The numbers are smaller anyway, and I only have 1 variable. But I do have 4 terms, and so the method that applies is factoring by grouping, where I'm going to look at this first half and kind of imagine splitting down the middle, first half and second half, and I'll factor out a GCF from each half. I'm going to drag my 3y squared and these outer parentheses, drag those along, I won't lose them. But now in my first half of this inner polynomial, the GCF is x squared, and that leaves me with x plus 1. In factoring by grouping, I'm hoping to get the exact identical parentheses group in the second half, x plus 1, and it looks like I need to factor out a negative 9 to make that happen. So again, I'm just carrying along the 3y squared in those outer parentheses, but then this inside part I can factor out x plus 1 group, and that leaves me with an x squared minus 9. Here I have the difference of squares, so I'm not quite done. This one factors as x plus 3 times x minus 3, and then everything else I'm just copying from the line before.